ابراهيم
دكتور
تحياتي. يبدو كاين واصل شيان اللينك بالخطا. دخل الان ولا بعده؟
موجود نعم.
ممتاز.
كله سامعينك.
يعني اعتقد انه نبدا الان.
Dr. Jim, can you start please?
Hi.
Hello.
Hello.
Mr. Jan, how are you?
Yeah, great. Where are you?
Are you okay?
Yeah, I'm fine. I just logged into the wrong session.
Okay, that's fine. It's good that at once I have noticed that you are requesting the link.
Okay, fine. I just find the old version, but I still can in.
Okay, that's fine. So we can start now. On behalf of all participants, I would like to welcome you again for the fourth day important this workshop, and let me welcome you warmly on behalf of Regional Center for Space Science and Technology Education, Western Asia, and Arab Union for Astronomy and Space Science, and all organizations which is shown in the slides. Again, I would like to just give announcement to all audience now and participants that soon, next 27th, we will start another workshop which is exactly linked to the GNSS. So you are requested, if you would like, we will announce it soon, and we would like to have you with this nice workshop. And please, Dr. Xian, it's your floor now, and you are welcome again.
Okay. Okay, thank everybody. Sorry for the late. I will talk about in this lecture called differential applications. So as you know, that GNSS was very widely used, but the accuracy is about at meter level, maybe 10 meter level. If we can use we call differential methodology, we can have more accuracy. So we will introduce this technology in this session. So why basically differential? As mentioned before, traditionally we can get we call standard position service of a GNSS user about 10 meters accuracy, roughly. I mean, and 20 nanoseconds timing accuracy. But if you an application that needs more accuracy, more integrity, more availability, and more continuously, if you want to have more accuracy, more performance, so they need some technologies. So we call differential GNSS. So differential GNSS means you can get the accuracy about for example 10 meters. You can to let them at centimeter level, even to millimeter level. So that is why you can use this accuracy. But remember, the for centimeter level, I mean centimeter level, mainly on moving applications. Okay, remember that. And for millimeter accuracy, commonly in stationary situation. Okay. For example, in this one, you will show that different requirements. For example, oceanic, en route, or terminal, or precision landing, the accuracy of the different systems. So let's look to the detail sessions. So the first part is about evolution index. I have a talk last time. I just recall it. So the differential is depend on you want to increase the performance of the GNSS. So for the performance of the GNSS, but I mean by the differential technology, what you can achieve in performance increasing is accuracy and precision. I hope you stay to remember what is accuracy and what is precision, and as well as availability, integrity, and continuity. So that is by differential technology, we can improve this kind of performance. So all in detail, I will give a outline like what is the concept and the correlation of the GNSS errors and code-based, carrier-based differential technologies, and the message format of the GNSS information. So the differential GNSS is a methodology to improve the positioning or timing performance of the GNSS using one or more reference stations at a known position. So this station, we call reference station, will equipped with at least one GNSS receiver. And these reference stations will provide information to the end user via link. So that means we will have a base receiver here, a base receiver. And for example, if this is you, for example, if you are here, and the base station will also receive the satellite. For example, this is satellite vehicle number 1. So if this is satellite, will sending information to the base station as well as to the user. So the users will receive this satellite information as well as some we call correction data. This correction data will transfer from the base receiver to the roving receiver. By using this correction data, the accuracy of the user can be increased. So this is the basic concept of differential technology. So the information sending through this data link include some raw reference measurements. So that means what the station has seen, and also integrity data. So for example, use or not use for each visible satellite. And some additional information including the location, the health, the meteorological data of reference stations, and all this correction to the GNSS satellite. For example, the clock, the information, or the data to be broadcast will forward to the users. So by using this information, the user know what has been received in differential station. So the different station also include the absolute or relative differential GNSS. The absolute differential position is to determine the user's position with respect to Earth center Earth-fixed coordinate system. For this system, each reference station must have accurate ECEF coordinate systems. In this case, for example, I use a hover or maybe landing. For this case, this base station must be very, very accurate. And then they will tell the information to the users. So if you use absolute DNS, this will be accurate. So another one is using relative. Relative means the base station is not accurate. So the users will only know how much is away from the base station, not a globally absolute position. Okay, so by this one, commonly, for example, if an airplane landing on aircraft carrier, actually we don't care. We don't care about where is the satellite, where is the airplane. We more focus on how can it landing on the ship. So relative differential positioning is to determine the user's position with respect to the corresponding reference of the reference station, coordinate system about the reference station. Maybe this absolutely position of the station is not perfectly known, but still you can know the distance. And another catalog of the DHS is how much the area can a system cover. The differential GSS can be served maybe for a local area, for a small region, or maybe a large for regional area, a very wide area. So the local GNSS only work for a very small geographic area, commonly about 10 to 100 kilometers. At this case, we commonly place one base station is enough. One base station enough for local. Okay. And for regional system, it needs to have maybe several. For example, each one will cover about 50 kilometers. But if you have many base stations, you will cover a large area. So that I mean, for the local one, probably one base station, and for the regional, maybe many base stations. And for the wide area, because we cannot place so many base stations, sometimes we use satellite to broadcast the differential information. So this is a picture of the regional. The regional commonly cover more than 1,000 kilometers. For example, a province, a country, such a case, and the wide area, mainly by satellite, such as the WAS of the USA and the IGNOS of the European Union. So the WAS systems is kind of this is a satellite similar to a base station, and this is you can think this satellite is just a base station, and they were sending the information from satellite to the ground. Okay, this is the correction. This is the correction data to the user. So we just put the base station in space. Okay, so this is make the differential technology to be widely covered. Okay, so this is the catalog. And the third catalog of the DHS is a code base or carrier base. Okay, the code based differential technology mainly relied on the GNSS code measurement. And it can provide about decimeter level position accuracies. Commonly, as our experiment approximate to 0.5 meter to about 1 meter by code differential. And the carrier-based differential GNSS rely mainly on the carrier phase measurement. The carrier phase measurement can provide about millimeter level position accuracies. The differential, the differential of the difference of the code and the carrier is what information is used to make the measurements. For example, if you use the code, okay, you will see this is code. This is code like the PRN code, like the key using the PRN code is similar to be key. So each chip length, each chip of the key, okay, this one is approximate to 300 meters. So the accuracy of the differential systems is about 1 meter to 3 meters approximately. This is by code technology. So if we make measurements, another way is to make measurements by the carrier. Okay, the carrier means that the length of the carrier is about 20 centimeters. And so the accuracy can be increased about commonly to 1% of it, about 2 millimeters. So this is the first one is by code. And the second is by carrier. Okay, so these two is different. So by using these two methodology, we can have different accuracies. But keep in mind that you can get the code measurement anytime as you like. If you want to make measurements of code, anytime you can get a code measurement. But for the carrier, you need to a coverage. Commonly, you need several I think about 10 seconds or maybe 1 minute to make the system coverage. So you need time to make average. So if you want to get information from carrier, commonly you need, for example, 10 seconds, maybe to 1 minute. Then you can get a position, get one position of carrier measurements. So the carrier-based GNSS commonly used in stationary results, or the rover that don't have high dynamics, don't have any cover on it. It's possible. So our cars, our vehicles, our trains, you can commonly use code, and our survey and the monitor station commonly use carrier-based technologies. So the GNSS of the systems, they will have lots of errors. By using differential, why the differential system can improve? Because the differential technology of the system is to depend highly on the spatial and the time correlation of this error. This error commonly include, because you know GNSS receiver, including the following 6 parts, I think I have mentioned in the first lesson. This includes satellite error, ephemeris error, troposphere error, ionosphere error, and the multipass and the receiver noise. So when the satellite, for example here, satellite, sending the information from satellite to user, there were a lot of errors in the space. But for the base station, okay, for example, for the base station and for the user, some error is correlated. For example, they pass the same ionosphere. So ionosphere of these two is same. They pass same troposphere. So this is also same. And the satellite sending the same data from the satellite clock, from satellite, same satellite. So they have same clock errors and the same ephemeris errors. So this error, because it's correlated. So when the base station finds this error and they tell the user by the correction data, then the user can eliminate these errors. But for multipass and for receiver, this is user dependent, because the user one may have multipass one, they have a building one, but maybe base station has a building two, so they totally have different multipass. They also have different receiver noise. So these two elements cannot be eliminated by the correlation error, by correction. So by the differential technology, the only first 4 parts of the errors can be corrected. So that means, for example, if this is the base station, this is the base station, this is base station, we call master station, and this is the rover station. But for you, you will know your true position. For example, x1, y1, and z1. And also you can get a measurement from the satellite. For example, you can know it's x2, y2, z2. For example, this is the information you know, you pre-know. So this is your location, and this is measure from satellite. Then you can know there have a delta x, delta y, delta z error. Or maybe you can write in different pseudo range. Pseudo range 1, pseudo range 2, etc. to pseudo range n. This is how much error according to your knowledge and your measurements. So this error means how much is the error introduced in the propagation stage. So then you can use this, for example, delta x, y, delta y, delta z, or maybe delta pseudo range 1, delta pseudo range 2, etc. to delta pseudo range n. This we call the correction information. And they send this correction information. Then if the user has a measurements about x, y, y1, z1, and they can plus your error, or maybe plus your pseudo range correction, you will get a true x, y, z value inside of these measurements. So okay, this information in most case about 10 meter, well, this is about 1 meter for code, or maybe 0.2 centimeter for carrier. Okay, this is how can we rewrite this information. Okay, so by the code base, you can know, for example, x. Okay, is if you want correct in position domain, so this is the error of your measurements minus x2, and using say delta x to correct the rover's measurements, you will get a correct data. So this information x, y, z here, x, y, z here. Okay, this is the information called correction data, and you will use this to transmit from the base station to user to make the position more accurate. Okay, so but they have two problems if you buy this position domain. It's because the different satellite Okay, you say this is satellite. It's different. Satellite from the base station and satellite of the user may be different. Your solutions, different solutions, is a combination of all satellites. For example, this is the solution one, base station solution. This is the error contains of all the satellites visible of the base station, but the error of the station, of the rover station, of the user is the error of these new satellites. Probably this is different, and this makes it more hard to make correction. So to solve this problem, commonly we use pseudo range domain correction to measure how much is the error introduced in each satellite, not for all satellites, but for each satellite, how much is the error. So how to calculate this one? Because we can use the, in this case, the reference station. The distance of reference station is equals to each satellite minus reference station, and we can calculate theoretically the pseudo range from satellite I to position of the reference. This is the distance we can calculate, and then we can make measurements of how much is the reference and your measurements. This is the true value you can calculate it. And the second part is the pseudo range you can make measurement. So this is the correction data of each satellite. So then for each user pseudo range measurements, you can add with this correction. Then you will get the final corrected user pseudo range. Okay, so this is by solving the problem in a pseudo range domain. That means we need to make measurements on how much is the error comes from each satellite, and then we make correction to the user. Okay, so commonly, if you're using this system, this is the commonly performance of a code-based differential GNSS. From the document, you may find if you're using the GPS only, okay, the clock maybe has 1 meter error, and maybe group delay 0.3, and for broadcast ephemeris 0.8, and the most part is about the ionospheric error, for example, in 7 meters. So totally the error will be approximate 7.1 meters if we combine all this error together. Let me say mainly because of ionosphere error. But if you use the differential technology, local area differential GPS technology, the broadcast will be eliminated, and the group delay will be eliminated, and then you will see we will still have a little bit in the broadcast, in the ionosphere or maybe troposphere, but the error comes at only millimeter or centimeter errors. But these two is same. These two is same. So totally, the error at the user side will be about 0.3 meters, and several centimeters per kilometers. For example, if your baseline is about 10 kilometers, so this error will be about I think probably about 0.5 to 1 meter. That is because if your base station and for your user this satellite, and if you are very close, so the satellite will sending the information to you and the base station in a similar methodology. So maybe this ionosphere or maybe this troposphere, okay, they are same. But if you are moving far from the base station, by them several kilometers, so the ionosphere and the troposphere of these two will be slightly different. Slightly different. So that means with the length increased, the error will be also increased. So let's turn back. For this case, you will find that the error is related to 1 to 6 centimeter per kilometer baseline. That means if you have longer baseline, then you will have more error. So by using this is for single base station. So if you have the large error, you can use the regional area. The regional area just use reference stations. They will have a big number of the base station, and also the base station will distribute it over a large area. And then if the robo station they move to any place, then they will find the results from nearby stations, or maybe combination of several base stations. They will make combination of all these correlation to give you I say average corrections. Depend on, for example, if you near to this base station 1, if the user is near the base station 1, they will get a value from base station 1. But if you move here, you will get base station 2. If you are center, your correction information will be the mixture of all this patient. We call this reference station network. We will have many base stations. And the wide area differential access, because each base station in the ground commonly can cover about 50 kilometers region about 50 kilometers. If you can provide for example all the China, for example all the US or maybe Russian area, so you need to put the base station and move it to the space. So we call this satellite-based argument systems, where you just move the base station move to space to let one satellite act as correction broadcaster, as a base station to the satellite. The satellite just sending the correction data to the user. So it is possible to send to achieve about a meter level accuracy over a very large region. So the general approach of this is broadcast the total pseudo range error, and it can provide correction for entire region rather than just one base station to solve about 50 kilometers. It's just all nations, all United States, or maybe entire China or entire Russia, entire US. This is a wide area. Okay, so let's look detail for these errors. So the wide area GNSS can eliminate the orbit error. The orbit error typically they have more focus on the radio component of the satellite. For example, the satellite can have the orbit, they can have the error about cross track and along track. Cross track is for example, this is orbit. The cross track, this is cross track, cross track, and this is along, and this is these three directions. So the error mainly happen on this radar components part. And from our experiments, the radar components part for the satellite, for the broadcast information, typically at 0.8 meter. And the wide area differential systems, they were sending all these errors, the orbit error, etc., all these errors from satellite to user, and then the users sending, and then the users receive and make correction, similar to by the base station. So you may see from here, they were sending the errors of ionosphere, atmosphere, and etc., so on, and sending this information. And also by differential applications, except for DGSS, we also can use the differential methodology to do altitude determination. The altitude determination, I will give these parts, for example, some concept and altitude principles and some methodologies. The concept of the altitude of the GSS is you can basic concept altitude is about PVTA here, PVTA here, PVTA. This A is altitude commonly for yaw, pitch, and roll. When you're using a GPS receiver, for example, if you use your cell phone, commonly you will get the longitude, latitude, altitude. But if you want to get the altitude information, for example, your direction, commonly your receiver will give you this information by a magnetic sensor, and they'll tell you where is north and where is south. But the altitude is more complicated, and it is tell you your raw, pitch, and roll, about your raw, pitch, and the raw. This is about the altitude information. It's not direction. It's slightly different. So how can we get this altitude information by the GPS? I will give you an example of altitude, raw, pitch, and roll. And we call this is raw. This is raw, and you are playing like this way. This is raw, and for this is yaw, and this pitch. This is pitch. These three things, three direction. So the definition of altitude is actually is with respect to the local coordinate. So commonly, if you're on the Earth, we can use the ground for the reference. This is how much you look. The positive rotation of the each axis can be taken to the clockwise direction. Look along this axis from the origin. So the magnetic compass will give you direction, but only direction. Direction is one concept of the altitude of the altitude, but only, for example, north and south directions. For example, for the compass, I think ancient peoples using compass in very ancient time, but it's only for direction. And they currently have modern magnetic compass. It's more complicated, and also we have the geo compass. As I mentioned before, the geo compass is different than magnetic. The magnetic is find the magnetic north by the magnetic field, but the geo compass is using to sense the rotation of the Earth, and you use this rotation of the Earth to be a fixed find a fixed north. Remember that there was a difference between the magnetic north and the true north. So if you're using geo compass, you will get the true north. It is different as magnetic north. It is different. It is different as magnetic north. These two things is different. Okay, so we can also use a geo compass to get the altitude information. So it's a little bit complex because we can use in this way to calculate. And now our compass, geo compass, become more and more small. For example, some is called optical geo compass. You can buy the fiber or laser technology to sensor more accurate, but also more expensive. And some is using about micro geoscope on maps to make it very small to sensor in north, to sensor your directions. And another thing, the third thing I want to talk is about celestial compass. You can find where is the north in celestial systems. We can use a lot of Asian celestial compass, for example, cross staff, etc., to find the north from stars. We have the modern celestial compass, by electronic and sensoring technologies. We can find north by modern technologies. Also, we can use a radio compass to find the altitude, maybe directions. For example, if your aircraft is fly on Earth, you can sensor the radios from the different stations. And by these stations, for example, the VOR, it's a omnidirectional radios on VHF channel, and by when your airplane is fly, you can censoring the radios, and these radios will give you directions. For example, the VOR will sending the two beams at 112 and 117 megahertz, and then for you can receive these two frequency, and then you can know where is the base station and what is the altitude corresponding in regard to this base station. So it's a navigation system for altitude determination. So when your airplane fly, when fly, they will tell you, for example, if you set to this value, they will tell you how much away from this result. And also for the inter-landing system, when your airplane is landing, also, and there was a beam of radio beam point to you, and then you will landing to the system. For example, you will say, oh, this fly up, down, and right. They will show you in your screen. That means you need to fly up and left, and this means you need to fly right and down. You will see a cross. Okay, and this is try to fly on the glide path. Okay, I mean this is correct. And these two, if you see those two pictures, you need to make adjustment. So this system is used for landing, but it's used radio to give you the altitude information. Also, we can use the GNSS, for example, the GNSS chips in our cell phone to give you altitude information. So, let's talk some. Sorry, excuse me. Can you be?
يا عم خلص مش هيكون محدش هينزل في العيد.
Sorry. Okay. It's fine. So let's continue. So we can using the GNSS methodology to determine the altitude also. That's for its case. If we can install several antennas, for example, antenna 1, antenna 2, and antenna 3 on your carrier, and then this carrier, this device will receive the satellite, many satellite information. For example, your antenna 1 will receive several satellites, 2 will receive satellite. So all this information will be gathered and stored in the altitude determination system. Okay, by use this one, for example, in this coordinate, if you flight, you will have a lot of different coordinates with tropocentric coordinate systems, and you have the ENU coordinate systems, and you can make transformation between the different coordinates. And the basic principles of the altitude determination is, for example, your antenna 1, we call maybe master antenna, and your antenna 2, because slave antenna, this antenna 1, this antenna 2, and this signal from satellite K, they broadcast the travel of this signal is a little bit more compared to the antenna 2. So that I mean, this one has more pseudo range. If you can make measurement of how much error the differential result from the antenna 1 to antenna 2, for example, antenna 1 minus antenna 2. If you're using pseudo range of antenna 1 minus pseudo range of antenna 2, you will get how much is the signal propagate more. So this is the SB, and this is the baseline. So by using this distance and this angle alpha, you can know the baseline. So that means the alpha equals to the lambda, that is wavelength of, and the how much of this delta pseudo range over the baseline. So I mean, this has relations between how much is the baseline with the baseline and the difference in the pseudo range. They have two have relations. So if you can know how much is the pseudo range, differential pseudo range is, you can calculate the baseline. So this is similar as the principle of the GNSS, differential GNSS. It's similar because the differential GNSS is to calculate the error between the base station and the user. But the altitude determining system is calculate between two antenna. It's similar. So if you can solve the differential GNSS technology, you can solve the altitude determining system. It's similar. So by using this one, I ignore something. Using this one, you can know how much the error it is. The step means the first is you need to know the measurement value of the GSM receiver and calculate what we call the float solution. This is approximate value of the SK times B. That is means how much is the two antenna is, and then get the integer ambiguity solution. The integer ambiguity solution means, for example, this is a wave 1 and this is a wave 2. They have this is the delta. This is the delta phi of this one. But remember, the delta phi is actually n plus this delta phi. Probably you ignore the n because you don't know what is how much integrity is. For the carrier, you can only measure about, for example, a sine wave, sine or negative sine wave. You can get only the value from -1 to 1. For example, you got 0.3, but actually you cannot calculate the value, for example, 5 cycles and plus 0.3. So you cannot calculate this one. It's called ambiguity. So I turn back. So we need to calculate integer ambiguity to find the accurate differential in the carrier mode. So then we can calculate how much the baseline is. After you calculate the baseline, you can correspondingly to calculate the altitude. That means only such kind of altitude can have this baseline. They have the relation between the baseline and the altitude. So for the differential GNSS, for the DGNSS, the way is if you use delta lambda, how much the error it is, and then you can calculate the baseline. We commonly call B, for example, a baseline. For example, the B. We are using the how much the delta phi error it is to calculate the baseline length. For example, how much is you away from the base station. But for the altitude determination, we are also measure how much the phase error it is, and we also know the baseline. These two things is known value. We can put the two antenna in a fixed distance, for example, 2 meters or maybe 1 meters. If we know the delta phi and the baseline, we can use this one to calculate calculate the alpha. This is the altitude. Only, for example, and I think this is the baseline, and this is the delta phi. You can use it to calculate alpha. This means altitude. So the working progress, working procedures of this altitude determination is a little bit different as traditional differential GNSS. Okay, so the first is to get measure the value from the GNSS receiver, and then you can use a lot of mathematical mode to get a very high accurate position estimations, and to use mathematical methodologies to get this value. For example, for single differential, for the single differential, what you will get is the differential of A and differential B equals to the degree times with baseline. And you can use this baseline to get a lot of calculations, and then you will got called flow solution. This is approximate value of it's because you don't know ambiguity, you only get approximate value of the position. And then to calculate the flow solution and use it to get integer ambiguity solutions. And finally, you will get the baseline. So there were many different methodologies. For example, most is lambda and Farah, etc., to determine how to calculate the each steps. It's a very complicated mathematical solutions, but it can be solved. And then finally, if you use, you can get the value of 35 and integrity value, you will get the altitude angles. So commonly, the error of the altitude determination of the GNSS is approximate at 0.1 degree. Are you gonna turn back? The error, for example, if you calculate the degree, for example, this is degree alpha. Commonly, the alpha accuracy by the GNSS is about 0.1 degree to 0.2 degree for 1 meter. If you have, if you antenna, your antenna 1 and antenna 2, this is separated for 1 meter. So by using this device, you will get the altitude determined at 0.1 to 0.2 degree in the altitude determination. This is approximate, approximate precision of the altitude determined system. So this is the error. I know something. Time limitation. Okay. The key technology of this part is a commonly we call lambda solutions. It's kind of methodologies because you need to do a huge amount of calculation. A lambda method is called the least squared ambiguity decorrelation and adjustment methodologies to reduce the calculation complexities. Okay, this is lambda. It's just to use some special decorrelation method to convert the searching area from a very long shaped elliptical curve to a more circle one to get it possible to be searched. And also we have some constraint lambda method it is to make limitation about because the two antennas maybe the installation is inaccurate, so we can have C lambda or maybe WC lambda methodology to increase the accuracy because of the match of the two antenna. For example, if you have an installation of the antenna 1, this is antenna 1, and also this is antenna 2, this antenna 2. So actually, theoretically, I say this is 1 meter, but during installation, probably it's 1.01 meter. So if you're using lambda method, this one will have error because it is inaccurate. But if you're using C lambda, this is constrained lambda, then it is make you possible to get the value because this has a constraint. So last I will talk about some applications for this kind of altitude determinations. They have many advantages because the altitude determination system is very high accuracy with low cost and a low accumulation error, and you don't need to initial alignments and very easy to assemble. For example, in this case, we have the mobile 3-dimension scanning measurement systems. You can use it. Sometimes you can see a lot of antennas GSM antennas in the car, and then they use to get altitude information because of 3D dimension scanning systems, and also for the satellite communication in motion. If you're, for example, if your car, for example here, wants to communicate with a satellite, so this direction is, for example, if you car rotation at this one, that means because you want to communicate with this fixed car, so this one you must turn right correspondingly. So there was an antenna of the altitude determining systems will monitor this rotation and automatically adjustment for this antenna with the satellite communication link. So for example, in this case, if your car turn left for 90 degrees, and then your antenna will also automatically rotate for another 30 degrees. So I mean, for example, this is 30 degrees left, and this one will be 30 degrees right correspondingly. And also for precision agriculture, for soil, seed, and harvest, it's also use altitude determining systems. For if approaching to harbor, the direction is very critical. Not only position, and also for landing, for aircraft landing, the directions, the altitude is also important. In this case, the GNSS altitude determination system is very critical. And for landing, they are using this thing. And also for some dynamic carrier, for satellite, for missiles, drones, and also for destroyer, they have lots of antenna, GNSS antenna installed in it. They can use it to make altitude determination. Okay, so this is the main part of differential applications. So let's can take a short break, and if anyone has Q&A, please tell me. I will see the chat message.
If anybody who wants to ask a question, please raise your hands.
The question is, first is how to get errors due to physical orbits of deterrence kind. Sorry, I cannot understand what that means, but I think probably you want to know the orbit error of the satellite. Actually, we cannot know it because it is a very important error in the GNSS system, because of the satellite has the satellite orbit has some uncertain. They have some errors, commonly about 1 meter, roughly about 1 meter error. So because of the satellite has 1 meter error, and that means the base, for example, the base station in space has 1 meter error. So correspondingly to your position, you will also have about 1 meter error correspondingly. So this error cannot be eliminated during the traditional GNSS receiver. But if you're using differential technologies, then the satellite, if the satellite has 1 meter error, then the base station also has a 1 meter error. Then the base station can tell the user that there is 1 meter error in the propagation stage. So the user can eliminate this 1 meter error according to the correction data. So by the differential technology data, by the different technology, by the correlation methodology, they can crack this error. The physical orbits can obtain after 18 days. So I'm not sure what that means. I think you mean that the orbit can maintain If you don't make modification, then you can have, for example, I think you still have this satellite in orbit. You may don't control it. Actually, according to the GPS systems, the GPS system constellation can maintain its autonomous status in 180 days. I mean that all the GPS satellite can maintain it by themselves, and then if it's unmanned for about 180 days, the system can still provide you information. But during the maintenance stage, actually every about 1 hour or 2 hours, when the satellite across a base, your monitoring station, across your ground antenna, the new ephemeris, the new orbit information is uploaded from the base station to the satellite. So actually, according to the ephemeris data, they should be updated every maybe 2 hours, the orbit information. So I'm not sure that I answered the question or not, but the orbit information from satellite to user will be updated every 2 hours by the navigation message.
Dr. Makram Ibrahim from Egypt, please.
Yes. Thank you, Professor Tian. And it is only a simple question about the precision of the measurements from the satellite. In general, for the GPS system, we have to observe from at least 3 satellites in order to have a signal. In case of the if we receive for more than 3 satellites, does it affect the precision of the measurements? Thank you.
Okay, a very good question. Commonly, theoretically, if we get 4 satellites, we will be able to solve X, Y, Z, and T of the system. So that means at least we need 4 satellites to make the fix from the GSS system. But if we have more satellites, for example, 5 satellites or 6 satellites, then the accuracy can be increased if you use least square methodology. So you just find about least square methodology, because if you're using 4 satellites, so we are using the errors of all these 4 satellites into final user position. So if you're using 5 or 6 or 7 satellites, then all these 7 satellites error will be averaged and then to the final users. So commonly, more satellite means more accuracy.
Well, but as you know, also for users of the GPS, they should receive up to, for example, 5 meters precision, for example. So you said now that as long as you receive from more than 4 satellites, you could receive with a higher precision. How?
Yes. If you receive only, for example, 4 satellites, probably your error will not be 10 meters. Probably maybe 50 meters, or in extremely case about 100-meter error. It is possible if you use only 4 satellites. If you're using 6 or satellites, probably you will get accuracy about maybe 5 to 10 meters.
Okay, good. Thank you very much.
Welcome.
Thank you, Professor Ibrahim.
Thank you, Dr. Makram. Dr. Jan, should we go to the second question? Or I see no.
Okay, Yeah, someone is raising hand. Okay.
Nobody.
Let's see. Yo, no, somebody. Taku, I can try to.
Tarek,
Okay.
yeah, Tarek,
Taku.
Tarek, please.
My sound here. I just want to ask: is there are measurements that can be measured only for one time? It doesn't have to be measured again and again in other several maybe signals sent from the satellites to the base stations, or it's all have to be measured continuously. Like every time we get a signal, we have to measure that error and correct the error. Thank you very much.
Okay. Commonly, the correction information can used maybe for, I think, for several seconds or minutes. It's okay, because you know the ionosphere above your head is only a little bit changed. So in practically, we think commonly we think I think error correction information for recent about 5 or 10 seconds, it is fine to make corrections. So if during the correction, if the correction data link is not so good, some early correction data is still possible to be used to make this correction. But if you use very long time, for example, a few minutes, it is unusable, because during this time maybe there was more error in the space, or maybe error in the propagation. So this is our preference. Commonly, we think every second you can get a correction. You can get a correction and comprehensive by using differential technology. But in practically, some delay is fine. Or maybe for 5 seconds or 10 seconds, it's fine. Is that clear? Okay. So if no further question, we can move on for the next part. Okay. Okay. So in the last part, I will mention about anti-jamming technologies. I think it's a very interesting topic. So why we need anti-jamming, and some types of jamming and the effect on the receiver and anti-jamming technologies, technicals. Why we need anti-jamming? What is jamming and anti-jamming mean? It is because if we consider the power, the signal power we received from the satellite, you can get from such equations. The power equals to what, and also the received power is commonly is I write okay, it's the power they send. The power of a satellite. This one is the power of the satellite, and the free space loss. This is the propagation loss. So after this one, you will get the receiver power at this equation. Now this is related to the distance and the lambda. That means I mean the frequency of the signal, etc. So the GPS actually they are sending this information by a 12 element airband 6-phase arrays. Then they were sending all this information inside this beam to the user, to the Earth. So remember, there was no information sending, almost no information sending on the back of the satellite, because this is useless. Because if the satellite sending signal back above its backside, it's no use. So mainly the energies of the satellite is focused to the Earth. Okay, but still this information, when they send from satellite to the ground, the signal is very, very weak. So we can calculate by the power link budget of the GPS L1. So actually, the GPS is sending the signal at about 25.6 watt. I remember this one, 25.6 watt. Okay, this is the antenna from the satellite. And if we consider the transmitting gain, that means, for example, if you are at 5 elevation degree, so you can have, because no information is sending from the backside, so then you will get a transmission gain at approximate at 13.8 dBi. So so that means if you are here and the satellite is sending the signal at 25.6 watt, and because you use beam antenna, it has also at a 3.8 dB more gain times. Okay, so totally for your user, you will get a signal. You will get a signal from satellite. This is about approximate to be 28 dB watt. This is the power of the GPS antenna's array send out. So I don't know whether you know what means 28 dB watt. What is this unit? 28 dB watts. It equals to what? Does anybody know? 28 dB watt correspondingly to how many watts? Do you know how many watts is 28 dB watt? I'll tell you. It is approximate to be 630 watts. You can use Debrick watts to watts, about 630 watts. You can make an imagination. You can make an imagination that satellite is sending a wave, an electronic magnetic wave at about 630 watts. Okay, do you know what device has such kind of high energy? 630 watts. I just tell you, for example, your microwave oven. Your microwave oven is working at its radiate energies at about 630 watts. So this is similar that on your head, you will have, for example, if you are here, on your head, each satellite will similar to be a microwave oven on your head. Almost almost you can think every satellite on your head there is a microwave oven sending waves to you. God bless you, and maybe Allah bless you. And you are not be burned, it is because during the space they have, okay, here, free space loss. Free space loss. The free space loss is during the propagation, during signal propagation. It has this negative 144 dB loss. So after to your receiver, commonly you can receive a power at negative 106 dB watt. This means for your receiver, this is approximate power you will receive. Okay, so for the link budget, this is the signal power you have received at approximate negative 160 dB watt. And for the background noise, this is background noise. I see here, background noise. You can calculate it by the value kBT. This is equals to K, T, and B. The K is Boltzmann constant, and T is the elemental temperature, and the B is the channel bandwidth. And for this one, I want to say that according to this one, GPS L1, you can get the background noise calculated by the KBT. This is negative 111 dB milliwatt. Okay, so by use this value, we previously also talked that the SNR of the GPS is negative 19 dB. Negative, very, very weak to the GPS signal is compared to the noise. So because this signal is very, very weak, so it is very easy to jab it to any kind of such a little bit strong signal. It's much higher than the noise. Then it will interfere the GPS receiver. So this is the problem. So there are many types of jamming. For example, let's see. For example, some kind of jamming, you can see deceptive jamming. Deceptive jamming, the first is we call the re-style jamming. So to regenerate, and the second is called just forward, just relay, or maybe forward. Maybe use another forward, just sending the data gear, fake news. And the other is use the generated jamming. You can manually regenerate according to the GPS signal. You can regenerate the signal. This is deceptive. For example, if the jamming receiver got this data, and they just, for example, this airplane, they get this satellite and they resend this data to user. So make the user think this is a true satellite, but it's a fake one. So it's called deceptive tracking. Another one is the oppressive jamming. Oppressive jamming is kind of device that's sending a very, very long signal, a very strong power signal. So it make the user, for example, the user here, this is the user here. Traditionally, they can see the curves here, but after jamming, they just get nothing. That is the problem. So after signal generated, it's very strong. So you cannot hear the signal from the GPS, but you can only hear the signal from the jammer. So, because the signal is at a very low band, so you can just sending a signal, for example, continuous wave, a single frequency signal, very single. For example, this one, very single frequency wave, or maybe multiple single frequency. We call continuously wave, multi-signal. They send some wave. For example, the GPS is what 1.5 giga. You're just sending a very strong sine wave of the 1.5 giga. Then the GPS will be blinded because what you hear is only the signal from the jammer. And some narrow band jammer. Narrow band jammer is the signal that only have about 10% of all the signal. For example, this the red one is the signal you want. This is the GPS signal. This is a GPS signal. But this is the jammer. The red one, sorry. The blue one is jammer. It just be very strong. They just send, even they have very narrow bandwidth. but it's still possible to suppress your signal. And for the wideband jammer, it will send a very large band to let all the band higher than you, so you cannot use it. High band jammer. Commonly, the bandwidth is more than 10% of the available bandwidth from the GPS signal. And also, the first type is called a matched jammer or multiple access interface. That is, that methodology is generate exactly same pattern of the GPS signal. It looks very same, but only the power is very strong. So it makes you to look like there was a GPS. And the last part is generated as a pulse jammer. It's sending a lot of pulse, and the spectrum of the pulse look like this one. Also, you can generate a very high power pulse and to let the GPS to be suppressed. Okay, so after this methodology is using, they have the jammer will make effect on the receiver. For example, the first is about jam to signal ratio. You can use how much about the signal, about interference signal over the GSS signal. We call jam to signal ratio in the dB unit. For the BDS, BI signal, BI branch, commonly they can have at least because the BDS use correlations. So naturally, the BDS system can afford SNR about 40 dB. So about 40 dB is fine, but if you more than 40 dB, it will be challenge for the GPS or for the Beidong. For the BPS B3 branch, it can afford to 47 dB. Okay, so when the very strong power jammer is sending, then in the receiver part, it will affect on the R front end, because you know the antenna will receive, and then we have amplifier here, here, and here. If the signal is very strong, then the amplifier will output very high power energies. Then this kind of amplifier will be decreased. So then it will make it out of range. And also the importance of ADC is because the ADC, when it have a lot of noise, it will decrease the effective resolution and the effective number of the bits of the ADC. And then the ADC only receives the signal from the jammer. The no signal from the GSS receiver satellite will be received. And during the digitalization, commonly the GSS use 1 bit ADC or maybe 2 bit ADC is very popular. But if your signal is very high dynamic range, signal is very strong, the 1 bit ADC is useless for the receiver. And also there was affected on the acquisition. Traditionally, if there were signals, you will find a peak. If no signals, there are no peak, ideally. But if you can use interference, probably you will get a false peak. I mean, a false peak here. A false peak here. You cannot get the data from a satellite. So it's increased the first alarm rate of the receiver. And for the tracking loop, similar, and that because the tracking loop only has a limitation, it cannot be more dynamic range. If you have a lot of interference in it, it will finally let the tracking loops unstable. To also effect on the bit error ratio. If there were lots of noise, the bit error will be increased, which will make the receiver cannot decode the data and then cannot make a right position. They cannot get the navigation message. So if no message, there will no orbit information, no time information, and then cannot make position. So probably you will get a result to get the error position, and the position finally there should be position A. But if it's jammer, probably they will get position B to get a fake news. If anybody interferes, you can let the object to get a fake one, to get a fake news, and now this one get a fake news. So it's a motivation from the weight root. So how to solve this kind of problems? Actually, we can use a lot of anti-jamming technologies. Okay, that include about anti-jamming by system design, pseudo satellite technologies, spectral filter technologies, receiver technologies, and integrated system technologies. So actually, from system view, if you want to do anti-jamming systems, you can buy the 4 methodology. The first is to make backup of the master control station and cross-link of the satellite autonomous run, and use direction antenna for regional augmentations, and use some new military code. And the first one is if there were interference to the mass station, you can put a backup, try to find a backup. And second is the satellite can have cross-link. If there are interference by the ground station, it's still possible to let the satellite communicate with each other to maintain the orbit information. For example, just some friend has asked, some listener has asked that the orbit, how long the orbit can maintain. Commonly, I want to tell you that by this cross-link over the satellite, the GPS can self-maintain, autonomous running for more than 180 days. And the third one is for the augmentations. For example, in this picture, this is a picture of satellite block 3 of the GPS. Sorry, block 3 of the GPS. You may find, except for the main beam, they got a spot antenna. Spot antenna. This spot antenna is above their head to sending directional beams to the regional augmentation. That means for if any place that were easily to be interfered, then the satellite will specially send additional power to the special area. And the last one is using some numeric code. And the second methodology is by some pseudo satellite technology. When the GNSS is not enough for positioning, you can still use some pseudo light to make enhancement, to make maintaining the performance of the GNSS receiver. And it still have some problem to solve. The first is what kind of platform you need, and if you use pseudo light, how to make self positioning of itself, and how to design signal. And the last is you need to let the receiver to be compatible with others. Third one is the called special filter technology. There were 2 methodologies. The first one is called power inversion algorithm. That means we can use a multiple antenna. For example, here they form a beam, from a shape. Then if there are any jammers coming, the beams will receive nothing, and only the satellite from here is fine. Satellite from this different place, satellite is fine. So that is if the jammer. So we use let the power to be inversion, and then no signal will come in. I think how to make a power inversion. I give a very simple way. For example, This is the satellite, and this is antenna 1, and this is antenna 2. So if we use power inversion, I think it's most easy way. For example, in this case, we will use a very easy methodology. For example, this is the jammer, jammer from this region. So if you may see this is the beam sending, and this is the beam sending. So if we use the signal equals to signal A1 plus signal A2, remember plus A1 plus A2, another is signal equals to signal A1 minus signal A2. So for this one, if the minus 1, because this 2 has same distance, so this satellite, for this satellite in the S slash, this one will make the this satellite equals to 0. And for this equation for S, because there's a addition from satellite 1 to satellite 2, but from this jamming, this one can be inversed. For example, this for A1 will receive this one, but for A2 will receive inversed. So for signal S, if this is half lambda, so the S will be make the jam equals to 0. Correspondingly, they have the beam look like this one. This side will no signal coming. Okay, so similarly, in this case, power inversion, if we use an antenna array, then the power can be shaping to specific direction to make some signal comes in without some jammer signal do not come in. And another method for spectral filter is use adaptive beam forming technologies. That means if you use multiple antenna, we can make enhancement to the satellite. So the first methodology is that the jammer decrease, and the second one is that the satellite power increase if they use antenna array method. This is the results. Okay, so commonly for anti-jamming antennas, you need an antenna array. For example, antenna array to do this one. This is the picture of a 7-element antennas, 7 elements array that to do the anti-jamming. So if you have 7 elements, you can eliminate the 6 jammers from 6 directions. It's make possible. And also this is another this is another type of the anti-jamming antenna. So by using spectral filter, the time domain filter, and frequency domain filter, you can filter out the signal from interference from time, interference from frequency, and the interference from different directions. So commonly in an anti-jamming receiver, the methodology from time, from domain, and from spatial, spectral, all the methodology is using to eliminate the errors, the jammers in the receiver. Okay, so by using the spectral domain methodologies, we can make design of a very complex part. For example, the antenna 1, we will get a matrix, and the antenna N will get a matrix with different weight, So when we consider all this weight, you will get the final output after the different weight. For example, the weight of the SA1 plus SA2, you can see this weight is 1 and 1. For SA1 minus SA2, you can think in this case, the weight equals to 1 and the negative 1. Similar, you can just give the different weight of different antenna to let the signal jamming to be eliminated. So I will show you the results just to use different weight to get the data, and the power inversion algorithm is to adaptively adjust the weight of each branch to minimize the output signal, to let the signal to output to be minimized, to be not interferes. So we will see the PI algorithm will introduce you may see this power inversion. This is about negative 92.68 dB decrease of direction from 150 degree. Because if we want to have a continuous wave standing at 150 degree, then this wave for the user seems to be disappeared. Because when the signal comes in from spectral, its direction will be decreased. In this signal from all this direction will be decreased for 72 dB. 72 dB correspondingly near to be this value. This is about equals to I think about 20. 2 times with 10 to negative 7. And also, but there was a problem for the power inversion, because if the interference is coming from this direction, if also the satellite is coming from the same direction, and then this satellite can be not seen also, because what the PI algorithm cannot distinguish from the interference and the satellite signal. If they coming from the same directions, then you will know nothing. Then you will know nothing about it. And then by the second part is by the first methodology is by receiver anti-jamming technologies. Commonly, we are mentioned for the high sensitivity anti-jamming technology. For the normally the BVS B3I branch, they can tolerate for maybe 47 dB of J over S for at least for 40.7 dB. But if you're using high sensitivity receiver, then the J over S can be increased for another 20 dB due to the high sensitivity processing. Because after high sensitivity processing, the noise floor will decrease. Similar to be jammer to be decreased. So this is by the receiver technologies. So by using these technologies, the anti-interference ability by improving the minimal equivalent signal to noise ratio. Okay, the last methodology is use integrated navigation anti-jamming. You can use GNSS as well as INS together. When you put these two systems together, if the GNSS is interfered, then the INS probably tell you that the value, the results from the satellite presence system is too far away from it should be. So we can use maybe loose coupled by the combination fusion information from the INS and the GNSS together, and then after integration, we will know, for example, if INS is error, so that means the GNSS is wrong. So probably you will make the system to adapt it to the jamming, even by loose integrated. Okay, also you can use tightly coupled integrations to put INS and GNSS information together. For example, in this case, you may see INS and together with the GNSS together, to calculate the INS, pseudo range, and Doppler together, and then you will, by this result, you will know if there was error or not. And also, you can use ultra tight or deeply loose coupled integration by the GNSS and INS together. That means fusion all the information, we will find the jammers. Okay, so this is the principles about how we solve the jamming technologies. Because I think the signal of the GNSS is very, very easily to be jammed. So all the receiver current, even your cell phone, they have some very simple anti-jamming technologies. And also in the military device, it is some components, especially for anti-jamming antennas and anti-jamming algorithm, is also in the military GNSS receiver, because you know that during the wartime, the enemy definitely they were jamming the GPS or jamming the BeiDou standard systems. So the anti-jamming is very critical in whatever in civilian users as well as military users. Okay, thank you. This is the second part of the lectures, and we talk about anti-jamming technologies. So if anyone has questions about this kind of technologies.
Thank you, Dr. James. There's a question from the Facebook I brought to you in the
okay,
chat.
fine. In the chat, okay. Oh, sorry.
Anybody wants to ask, please raise your hand.
Okay. In the GPS signal, the SNR and the CN. Sorry. This is CN0. CN0, not CNO. CN0. It is a little bit different. SNR is the signal to noise ratio. It's corresponding to noise. Commonly, the SNR of the GPS, for example, the GPS is -19 dB, negative 19 dB in the SNR, and for the CN0 is carrier to noise density ratio. It's irrelevant with the bandwidth. So commonly, the carrier to noise density ratio is 44 dB hertz for carrier to noise density ratio. It's signal over noisy density, not noise itself.
Is there any question, please?
Okay, I write a brief letter, a brief note.
Yeah. Let's remind all of you that Dr. Jian will be with us next week. All the time will be started at 5 p.m. Amman time, not 4 p.m. like this week.
$5 p.m.? No, 5 p.m. I
5 p.m.
3 p.m., right? Not 5 p.m.?
You said 5 or 3 p.m.
3 to 5 p.m. I'm not quite sorry. Okay, I will make announce little bit. Sorry, make 3 to 5. I suggest for Dr. Hani about 3 to 5 p.m. in Jordan time.
Yeah. Then it will be 3 to 5 p.m. Jordan time.
Yeah, maybe you may thanks if you can make an announcement a little bit later for the time and the date.
Please, the announcement will be in our website.
Okay, fine. Okay, thank you. If no questions, okay, thank you.
If there's no question, please let me again thank Professor Tianjin from China Regional Center for Space Sciences Education for Pacific and Asia. We hope that we will meet you next week in a new course. It was a very interesting course, very important for all engineers in GNSS. Wish you a happy week. Will have here holidays, for days Eid al-Fitr. I wish all participants happy holidays, and let us pray that we will meet when coronavirus will disappear from all the world. Thank you again, Dr. Tian.
Okay, thank you and welcome. Shukran.
Shukran, Dr. Naj. Thank you.
Thank you.